works. And then I'll discuss some recent results, well, relatively recent results on some free boundary models. Firstly, with the local diffusion, and then with the non-local diffusion. So now let's start with Fisher's work. So in a very well-known paper now, 1937 paper, so Fisher used this semi-linear parabolic equation, or we call reaction-diffusion equation, to describe the propagation of a certain gene in a population. So here, the unknown function u is a function of time and space location x. It represents the density of the population that carry that particular gene. It's called an advantageous gene. And d is a positive constant representing the diffusion rate. So assuming the individuals of the population move randomly in space, following the Brownian motion law. So then you have this diffusion term. And here the right-hand side is a quadratic function of u with this constant a, again a positive constant representing the net growth rate of the population. And Fisher noticed that, so to solve this partial differential equation, you can look for a special kind of a self-similar solution. And then, if you look for such a self-similar solution, where v is a one variable function, you substitute this into equation 1, and then the PDE becomes an ODE. But this ODE, Fisher could solve these, well, according to the value of the parameter c introduced here. So if c is greater than or equal to this particular value, c0, obtained by using the two parameters a and d, and he could obtain such a solution. And he gave a name for such a solution called wave of stationary fall. So the reason is that for any fixed t, you look at the graph of this solution as a function of x. So the graph looks similar because it's generated by this one function v. But when t changes, so the graph moves without changing its shape. That's why it's called a wave of a stationary fall. And of course, now we call these kind of solutions traveling wave solutions. And c is the wave speed. And what's very important is that, so Fisher believes that this number c0, though for any c greater than or equal to c0, you have such a traveling wave with the speed of c, but he believes that the minimal speed of c0 should be the spreading speed of the population carrying the particular gene. So basically, he used this model with some analysis and then proposed that, so the c0 is special. It should be the spreading speed. But he did not provide a rigorous proof to that. He did have some analysis supporting the claim, but it's not a rigorous mathematical proof. In the same year, there's another paper appeared, now of another classical paper by, well, we call it KPP, standing for Kolmogorov-Petrovsky and Piskunov. And they were motivated by the same kind of a problem, but they independently proposed a similar reaction diffusion model. And the only difference from Fisher is that they used a more general kind of function f of u. And of course, the one used by Fisher, we call Fisher nonlinear, satisfies these conditions. And they proved a similar result for c greater than or equal to a particular value c0, now because they use f, so instead of a, they have derivative of f at 0. For c greater than or equal to this value, and they can prove so 2 has a traveling wave solution with the speed c. And they also demonstrate that this c0, minimal speed of a traveling wave, is special. How? If you look for the solution of a 2 with this initial function, this characteristic function, they can prove that the solution, unique solution with this initial condition, converts to the traveling wave solution with the minimal speed, c0. So WC is the traveling wave with the speed of c, but this is WC0 in that sense. So roughly speaking, so they proved that the solution U for large T really looks like this traveling wave moving with the T. So this, again, is not a rigorous proof to say the population here propagate with the speed c0, but really, if you choose these initial functions, special initial population distribution, and then indeed the solution converts to this traveling wave with the speed c0. So c0 is special, and this result supports the claim by Fisher here. Now, these results from 1937 didn't attract the deserved attention for over 10 years. Maybe it was because the Second World War, or maybe they were too ahead of the time. But in 1951, another important paper appeared, and that attracts a lot of attention. So that's the work by Scanlon. And he observed that in the spreading of a masquerade in Europe, so that's masquerade in Europe, that's the story. So the observed data of these spreading of masquerade demonstrate a constant spreading speed. How? Well, so Scanlon used this map, appeared in a book in 1930. So that has been available even before the 1937 paper. But no one thought this would reveal some mathematical thing. You look at this map, it doesn't say anything, mathematics. But Scanlon did one thing, very smart kind of a consideration. So you look at this map, there are many closed curves here. And actually, with each closed curve, there's a year attached to it, indicating the spreading front of the masquerade in that particular year. So people followed their expansion, and for every year they observe where's the spreading front, and they followed these and got this map. So that's a map of data for over 20 years, from 1905 to 1927. Then what did Scanlon do? And he just estimated the area inside each closed curve. And so he got an area changing with the time. And then he took a square root of the area and say, look at how this square root of the area changed with the time t. Well, he plotted them onto the time and the square root area plane. I found all these observed data over 20 years lie on this straight line. So in other words, so this function is linear. Well, that's really special. You look from this, you look at this map, and you observe something interesting. So this curve is a line, straight line. But why square root a? Well, if this, for example, is the shaded area is one of those enclosed by the observed closed curve, and if you draw a circle including the same area, then the radius of the circle, of course, it depends, R depends on T, on this particular T, has an ecological meaning. So this R is called the range radius of this, well, this shaded area in ecological term is the population range at a particular time T. And this R is called range radius at time T of this population. Well, these species masquerades. Now in mathematics, of course, we know square root AT equals this universal constant times R of T. So therefore, square root AT is proportional to the range radius. The range radius basically it is a quantity that gives you a rough idea, like an average distance of the front from the original place. So now Scanlon's observation really says that the range radius of masquerades increases linearly in time. And if it's linearly in time, by looking at that, then the slope of this straight line would be the rate of increase. And this rate of increase, well, that's the spreading speed. So the range radius increases with a constant speed c. Well, what is c? Well, here, of course, is the slope. But if we relate this observation to this earlier result of Fisher and Scanlon, well, all makes sense. So they already claimed using the mathematical model that the spreading has a speed c0. Okay, after this observation by Scanlon, so people looked for other field data, and they observed there's a field data for the spreading of a Japanese beetle in North America, and they did the same thing, and they found this curve, well, straight line as well. So not at the very beginning, but eventually the growth curve of the range radius is linear in time. And this bird house range in North America is spreading followed a similar rule. So all these support the theory that spreading has a constant speed. And then, so these phenomena got rather convincingly proved by this result of Aronson-Weinberger from the University of Minnesota in 1978. So they looked at a more general situation, and not only in R1, but they considered the situation in a general n-dimensional Euclidean space. A similar equation, well, actually in their paper, they considered more general f of u, including this special case. But today, for simplicity, I'll just consider the case with this Fisher nonlinearity for the convenience of comparison. And then they looked at this problem with the initial function. And of course here, so we try to understand U as the population density of a certain species. And if you want to use these to study the spreading propagation property, so we assume that at time equals 0, the population distribution, the density U0, is a function which is locally concentrated. In mathematics, we say it has a compact support. That is to say, the set of space variable x, where U0 is positive, is a bounded set in Rn, and therefore it is pre-compact. So then you look at the locally concentrated population, and you want to know how the population spread with time using this model. And they proved rigorously this result. So in the set, inside a ball of a radius roughly C0 times t, well, there's an arbitrary small number epsilon. So inside of this ball, the solution is close to 1 for large time. Outside of that ball, the solution is close to 0. And this ball, we say, is a radius change with the time, like linearly. And now, if we try to, to understand the population range, well, as time equals 0, the population range is where the supporting set is for the initial function. It's a bounded set. Unfortunately, for this model, and because of the maximum principle, when t is positive, the set of x where the solution is positive is entire space. So therefore, you cannot say that the population range immediately becomes the entire space. To circumvent this problem, the usual way to do it is to nominate a small constant delta, and you use this set to represent the population range. It's a change with the time t, but this set is always fine. And then the range boundary would be the boundary of this set, and we know that's where u equals delta. Now, if we want to understand how this range boundary or spreading front evolve with the time, so that's like you look at these. So you want to see how these boundary evolve, and you try to use this range radius, and then what can you say? Now, really, this result implies that this spreading front, the range boundary, for large time is contained in this spherical shell. So this is a spherical shell with the thickness compared to its radius is small because epsilon is small. And the radius of this spherical shell is roughly C0 times t. And therefore, this range radius for this population range is roughly C0 times t, growing linearly with the speed C0. So therefore, C0 is indeed the spreading speed of the species U. So this result really convincingly proved that C0 indeed can be understood as the spreading speed. And how to determine C0? Well, the same kind of thing. You look for a self-similar solution or traveling wave solution, and you solve this problem. And again, it's like Fisher and KPP observed the same thing. For this problem, when C is greater than or equal to some C0, C0 should be really 2 square root f derivative at 0 times d. And in the case of Fisher nonlinearity, so this is exactly 2 square root AD. So the spreading speed is indeed C0 as claimed by Fisher. But here, so this is a rather convincing proof. But are these theoretical results really useful? And indeed, people actually, so in different research, people looked at different species. They followed their spreading and compare the theoretical results to the observations. And of course, in ecology, for the parameters, there are two parameters, A and D in the model. And so these are not mathematical papers. So they use a kind of epsilon to represent A, the growth rate. And also use D to represent the diffusion coefficient. For these problems, for a given species, you don't get a very accurate parameter. Actually, you only get a range. For diffusion rate, you get a range. And therefore, for the theoretical result using these formula, you get a range for the spreading speed. And for the observation, again, you don't get just a unique value for the spreading speed. You get a range. You can say for the majority of the cases, the theoretical result is very close to the observed result. Well, except these cases. So this is not quite right. So the observed spreading speed is much faster than the theoretical one. So nowadays we might guess this perhaps is caused by long distance dispersal, this kind of thing. Anyway, we will look at this later when we look at non-local diffusion model. So anyway, so this model started by Fisher and KPP gives you a theoretical spreading speed, and that is a rather useful one. Gives you a good estimate of the spreading speed of the species. And you compare with the observed speed, they are rather close. So now, of course, in mathematics, mathematicians does not stop at just a result like this by Aronson-Weinberger. And people looked at this early result by Fisher KPP. They want to say, can we extend this result for more general initial function and also better estimate of these small OT term? That was achieved, and that's what is the next result. So if you look for in high dimension, you look for rigidly symmetric solutions. Indeed, you can prove that the solution converges to the traveling wave with the minimal speed C0 in that way. That is a much accurate estimate. And this small OT term actually is figured out using this log T rate and with these coefficient, diffusion rate D, dimension N, and these same C0. Now, this is for the rigidly symmetric case that also gives you a good estimate for non-rigidly symmetric case. So for this sharp estimate with logarithmic shift, so this is called a logarithmic shift. In dimension 1, that was first proved by Bramson, another University of Minnesota mathematician. And actually that was proved by using a probabilistic method, not an analytical method. And the high dimension case was proved by Gartner, and again by a probabilistic method. But of course, now there are also several analytical methods available proving these results. And here, that's a remark for non-rigidly symmetric case. And in the non-rigidly symmetric case, and the population range is given by that one, and you can show, so the boundary of this set is contained in this spherical shell with finite thickness, and the radius of the spherical shell is roughly this. So the main term is the C0T, but there's a correction term, a log T term. So a high, yeah. So when you look at a large T, this is a perturbation term. This is the main term. And then now there are much sharper results for this extension. For example, this recent result shows that So instead of this one, and you can expand more. So you find, so the perturbation term is these. That's in one space dimension, constant term, and you have a small order term. Yeah. When t goes to infinity, the term goes to 0. So very accurate estimate. Anyway, now, so let's move to this free boundary model. So why we want this free boundary model? So the reason is because, so the classical model, so as we mentioned here, to find the population range, you cannot use the natural definition where u is positive. You have to look at u greater than delta. So basically that says, so this classical model gives you the spreading speed, C0. It doesn't depend on this delta. However, it doesn't tell you where is the spreading from, which is usually very important in practice. So like if we consider the spreading of a virus, for example, so we are very sensitive on where's the front, right? Like this COVID. So we want to know where's the epidemic front. But this classical model does not provide that information really in itself. So now, so this model is just to try to get rid of that, that shortcoming of the classical model. So we use the same equation, but assume that hold over the population range, which changes with t. At the boundary of the population range, we assume the population density is 0, and outside, of course, there's no population. And we have an initial population, U0. But, so if the population range or the domain of the partial differential equation changes with time, and then you need another equation to make this problem well posed. And this is the extra equation. I'll explain what's the physical meaning of this equation in the next slide. But here, so everything is just the same as in the classical model, except now the population range is given explicitly in the model. And the price we pay is that, so this problem, mathematical problem, needed one more equation, and it's much more difficult to handle because in mathematics, we call this a free boundary problem. And everyone working in partial differential equations knows that free boundary problems are very difficult to handle. Now, why this equation? And that actually is borrowed from a classical case. So if f is identical to 0, then this problem arises in a very different setting. In the investigation of melting of ice in contact with water. So this omega t, in the classical sense, f is identical to 0, represents the water region. It's surrounded by ice, and U is the temperature of the water. And this problem is called the one-phase Steven problem. And because it's difficult, even f identical to 0, this is a very difficult question. And the regularity of the solution has been an open, difficult problem for many, many years until so the research of these well-known mathematicians that solved that problem in the, I think, in the 1970s. Now, let me explain what's the meaning of the free boundary condition. So here, it means any point on the free boundary. So gamma t denotes the boundary of omega t, the population range. Any point on the free boundary moves in the direction of the outward normal at that point of the boundary, and with the velocity proportional to the gradient of the population density with respect to x at that point, boundary point. So that's the meaning. And if we are in a spherically symmetric situation, so solution is radially symmetric, and therefore the free boundary becomes the sphere. A sphere, of course, is a radius of the sphere is changing with the time. And then in that special situation, these free boundary condition can be written in that way. So the change rate, the rate of change of the radius is proportional to these partial derivatives evaluated at the boundary. Now, what's the biological meaning of these free boundary conditions? See, these joint paper with my colleagues here, and we deduced these free boundary condition from a biological assumption. What biological assumption? We assume that at the sperm front, in order to expand the population range, the population makes some sacrifice. And so that the rate of expansion is proportional to the loss of a population there. So if we make these biological assumption, we can derive these kind of free boundary equation. But is this assumption reasonable? We believe it's reasonable. However, there's no biological rule to say, well, this assumption is correct. So this is just based on a reasonable assumption. It's not a law. So now, anyway, coming back to the problem 6, the free boundary problem. So we can show, this is joint work with Professor Zhengming Guo from Henan Normal University. We can show that the problem always has a weak solution. And what's the long-term dynamic behavior of the solution? So in joint work with Professor Hiroshi Matano from Japan, Tokyo, and Dr. Professor Kelly Wang from Wuhan University, we proved the following result. So this model 6 has the following property. So the population range always expands with time. And for the free boundary, the boundary of the population range, outside of the convex hull of the initial population range omega 0, it is smooth. Moreover, for large time as t goes to infinity, because this is increasing, the population range is expanding, so there's a limit. The limit, well, as I said, the limit actually is this unit. So when t goes to infinity, omega t converts to this set, and we have a dichotomy. There are only 2 possibilities. Either this limiting set is a bounded set, or it is the entire Rn. See, for example, this cannot be a general unbounded set. So it cannot be half space and so on. So if it's unbounded, it has to be the entire Rn. Otherwise, it's bounded. Moreover, when the population range converts to a bounded set, the population density converts to 0 uniformly. So that really means the population vanishes eventually. In the other case, when the population range converts to the entire Rn, the population density converts to 1, which is the carrying capacity. So this is the situation that the population spread successfully. So we say this is a spread and vanishing dichotomy. Furthermore, in the second case, we can come back to see more about the free boundary. For large time, the free boundary becomes a smooth hypersurface, closed hypersurface, contained in this spherical shell with a finite thickness. So the thickness is bounded by the diameter of the initial population range omega 0. Moreover, this range radius converts to infinity linearly in time. So this ratio converts to some positive constant. And now this, of course, tells us this new model also has a spreading speed. It's a C0 star. And how to determine this C0 star? Again, you look for traveling wave solutions. So this is from a joint work with the Pendulum Law of Shanghai Normal University. And for the free boundary problem, the traveling wave solution satisfies these. So now Q is defined on this half line, not the entire line. And apart from the two boundary conditions, the free boundary condition gives you a third additional equation here. But this problem has a unique solution pair. So this C0 star, the speed for the traveling wave is the spreading speed, proved here. Now to distinguish this traveling wave from the normal traveling wave, we call it a semi-wave because it's defined over a half line. Now I should mention that, so these free boundary kind of thinking, modification of the classical model started with this paper with Professor Zhigui Lin of Yangzhou University about 12 years ago. And that was the first paper to use the free boundary model. And that was in dimension 1. So where we don't have to worry about this regularity of the free boundary. In dimension 1, you don't have to worry about the regularity because the free boundary becomes 2 points of the boundary of an interval. Now this numerical simulation is from a paper by with Shuang Liu and Xinfeng Liu from a University of South Carolina, gives us an idea about how this population range evolve. So if omega 0 is this annulus with a cut, so it's this one. And then when time t increases, so you can say we don't always have a smooth free boundary. You can say we have singularities here. So gamma t in these graphs are represented by the red curve in dimension 2. Now we can say, so outside the convex hull of this set, so the free boundary is smooth. But inside, there can be singularities. And time increases further, and then we have, so these part, and then these shrinks to this, the whole. And for t even larger, the whole disappears. The free boundary becomes a closed smooth curve. And it evolves. So then like that, what is said here. So it's a free boundary is contained in a spherical shell whose radius grows to infinity linearly. So that is in the spreading situation. And that's the classical traveling wave with the speed C0, and now the new semi-wave with the speed C0 star. And also we can look at what happens to the solution when t goes to infinity. And we can show in the rigidly symmetrical case, the solution indeed converts to the semi-wave with a unique speed C0 star. And the range radius, and we have this accurate estimate. We have a log t correction term from this C0 star t. And this C0 star is the spreading speed, C1 star is determined through these complicated formulas. If without reduced symmetry, we can use a comparison result to show that in the general case, the population range boundary. So the range boundary is contained in a spherical shell with a finite thickness. And the radius of the spherical shell is roughly this. Now, what's the relationship between the new model and the classical one? The new model is 6 with the free boundary condition, and the classical one is 3. So in this paper with the Guo, we proved that as mu goes to infinity, the solution of the new model converts to the solution of the classical model, if you have the same initial function. And the speed as well, the new speed C0 star converts to the speed C0. And as mu goes to infinity, this increases to C0. Really, that means for finite mu, C0 star is less than C0. So really, these results indicate that the classical model 3 is the limiting problem of the free boundary model when mu goes to infinity. Now, what's the biological meaning of mu in this model 6? Well, the biological meaning of mu is the following. So 1 over mu is proportional to the population loss near the boundary. So remember, we can derive 6 from the biological assumption that near the spreading front, there's a population loss. Now, if the population loss goes to 0, so mu goes to infinity, the population loss is proportional to 1 over mu. Then the model converts to the classical model. Basically, in the classical model, you don't assume any population loss when the population spread. So now if we compare 3 and 6, and we found they have similarities. The shape of the front, for large time, the front gets more and more like a sphere in high dimension. And both models give you a spreading speed. But there are also differences. Of course, the major difference is the following. 6 tells you the location of the front. That's the free boundary. 3 does not. And also, if you look at whether the spreading will be successful, the classic model says it's always successful as long as the initial population is not identical to 0. But the 6 tells a dichotomy. So the spreading may or may not be successful. There are 2 possibilities. If the initial population is small, then the population will vanish. If it's large, then it will be spread successfully. And actually, we can obtain, if you choose this kind of initial function using sigma as a parameter, you can show there's a critical sigma star, so that for sigma less than or equal to this critical value, you have a vanishing. For sigma greater than this critical value, you have spreading. So this joint work with the Pendulum Law, and this is Maureen Zhou from Nankai University. And there's actually another deeper difference. If you look at the logarithmic shift, you can also notice this difference. In 6, the coefficient of this log t term has a factor n-1. So in dimension 1, this correction term disappears for the model 6. But that's not the case for 3. For the classical model, the correction term is there even if dimension n is 1. So now let me quickly look at the case where we have a non-local diffusion. So 3 and 6 are the very basic models, and actually they are extension in several directions, looking at the systems equations and also the situation where the environment is heterogeneous. In 3 and 6, really, it models homogeneous environment. But today, I don't want to look at extensions in these directions. Instead, I want to focus on their extension in the direction of non-local diffusion. So replacing these random diffusion by non-local diffusion, and what happens to these models. And the non-local diffusion has been observed to play a very important role in many spreading phenomena. So this is a phenomena about evolutionary spreading. So they observed that if you include the long-range dispersal in the assumption, then you have accelerate the spreading. So now, why we call this local diffusion, the model 3 and 6, and what's non-local diffusion? So local diffusion really is because in the modeling process, you discretize your problem, you divide us, say in dimension 1, you divide the space into equal length, the intervals, small intervals, you divide the time into small time steps. And then to deduce this diffusion term, and you assume that individuals in the population move in space randomly. Moreover, they only from the current time to the next time step, they only move to the neighboring block, neighboring interval from their current location. So neighboring is the key, why it's local diffusion. And they move to either to the in dimension 1 left neighborhood or right neighborhood with equal probability half. If you do that, and after a limiting process, you derive this term, diffusion term, in your equation. Now, if you assume an individual at X can jump to any other location with a probability J, and then, so this is non-local. So it from the current time to the next time moment, you may jump to far away places, not the neighboring interval, small interval. And then this is non-local diffusion and determined by this probability kernel. And if you use these in the modeling process, instead of this, you get this integration term, integral term. And this is called the non-local diffusion operator. And then 3, with these replaced by this non-local diffusion operator, you get this, equation 9. Everything else we assume is the same. So if you say, for example, is still the Fisher nonlinearity. Now, what kind of a probability function do we use? Well, very often people assume it's a continuous, non-negative, an even function, and normalized. And then what's the difference when you change the local diffusion to non-local diffusion? Well, depends on what kind of a kernel you choose. And it turns out that this thin-tailed kernel notion is very important. So if this kernel has this problem for some positive lambda, this integral is finite, then we call J thin-tailed. Basically, it says the graph of J at x positive infinity goes to 0 very fast, at least exponentially. Otherwise, these won't converge. Otherwise, you call this kernel function fat-tailed. It turns out that for equation 9, for thin-tailed J, its dynamical behavior is similar to 3, where you use local diffusion, but work from many, many people. But for fat-tailed kernels, there's difference. What difference? So for any kind of a kernel satisfying what we said, the properties, you can show similarly to the local diffusion case, the population density converts to 1 when t goes to infinity. And then you look at how the population range changes. Now you make this similar kind of assumption. You nominate a small delta. You look at the boundary of this population range, and you look at this. So this interval GH is the smallest interval containing the population range. And then you can show So this ratio and this ratio convert to a constant, finite constant, if the kernel function is a thin-tailed. Otherwise, the limit is infinity. What does that mean? That means the spreading is accelerating. So we say this is accelerated spreading. And this work about Garnier even checked how fast is the spreading in this case. And if J behaves like that, that fat-tailed, and the spreading front goes to infinity, so this goes to infinity like exponentially, not linearly in time anymore. And if J behaves like that, if beta is greater than 1, this is still a fat-tailed kernel. And then, so G go to infinity like t to the power of beta greater than 1, so faster than linear. And for fractional Laplacian, and you have such a kernel, and this spreading is again exponential. So now let me look at the free boundary problem. So in the free boundary model, we can also replace the local diffusion by non-local diffusion. And then based on the biological assumption, we have to change the free boundary equations accordingly into this one. And this is the assumption for the initial function, assumption for the kernel function, the basic assumption, as I said. And let's focus on this Fisher nonlinearity. This explains why we use these kind of a free boundary condition. So that is again assuming that the population range expands with a rate proportional to the population loss. So that's the population loss. And the model was actually appeared independently in 2019. This is our work, and this is a work of another group, people from, I think, Argentina and Spain. I know Fernando very well, and we had collaborations. But at that time, we didn't know each other's work. So that was really rather independent. But they consider the case F is identical to 0. And we focused on the case F is this Fisher nonlinearity. So therefore, the dynamics, long-term dynamics of these two cases are very, very different. But we independently used the same kind of free boundary equations. Now, what's the long-term behavior of the non-local free boundary problem? Well, we proved this is a joint work, that work mentioned in the last slide, 2019 paper. So if you look at it here, so this is a parallel to the local diffusion case. Spread and vanishing dichotomy, and we also have spread and vanishing criteria. These are more or less parallel to the local diffusion case. And the big change appears when you look at the spreading speed. So we found this condition on the kernel function is a very important, a threshold condition. If this is satisfied, then the spreading has a finite speed, C0. Otherwise, we have accelerated spreading. So this is proved in joint work with Fang Li from Zhongshan University in Guangzhou and Maolin Zhou from Nankai University. And how to determine these C0? Well, we again look for traveling wave solutions, and now we have to solve this problem. We proved this problem has a unique solution pair when J1 holds. If and only if J1 holds. And in another work with Wen Jianli, who is my postdoc here, and we checked. So in these cases, can we get a more accurate estimate? So if we look at these kind of kernel functions, when near infinity, it behaves like h to the power of minus alpha. We do get a more accurate result. So now let's say for these kind of kernels, the basic assumption means alpha greater than 1. Satisfying J1, the threshold condition governing whether you have accelerated spreading is equivalent to alpha greater than 2. So we proved that when alpha is greater than 2 in these cases, so when alpha greater than 3, so this difference is bounded. When alpha equals to 3, this difference is no longer bounded. It goes to infinity at the rate of log t. When alpha is between 3 and 2, that's again the case J1 holds. We have a spreading speed, but this difference is not bounded. The difference goes to infinity at this rate. When alpha is between 1 and 2, so this is satisfied, but J1 is not satisfied between 1 and 2. We have accelerated spreading. Then how fast does they go to infinity? We proved that when alpha equals 2, it goes to infinity at this rate. So faster than linear is t times log t. When alpha is between 2 and 1, it goes to infinity even faster. It's t to this power, which is greater than 1. So this accelerates spreading. I think that's all. Yes. So finally, a final comparison. So between 9 and 10, so accelerated spreading, the new phenomenon occurs to the nonlocal equation without a free boundary if and only if the kernel is not a thin tail. And for the free boundary model, this new phenomenon occurs if and only if J1 is not satisfied. This J1 and J thin turns out to be comparable. So J1, J thin implies J1. So really comparing these two models to say is that, so the one without a free boundary is more readily to spread with accelerated spreading. So though both can have these new phenomena. But if we compare with the non-local diffusion model, whether it's the classical one or the free boundary one, you never have this accelerated spreading. They always spread with a finite speed, if spread happens at all. I think I'll stop here. And there are some more recent works on systems of equations with the free boundary and the non-local diffusion. Thank you.
Thank you, Professor Du. Any questions? Vamos perguntas?
Dude, this is not a question, but just to say thank you. Very nice talk, very clear, very interesting subject. Thank you very much.
Thank you.
I have made a问题。谢谢杜老师。Thank you again, Professor Du.他们有些留言。那好吧，杜老师，你再休息会儿吧。
Okay, thank you.
谢谢你，再联系。
Hope someday I can visit your university and meet people in person.
OK， 今天你要是过来 访问的话，我们也非常欢迎你。
可以，拜拜。
可以了，
也
再见。Bom, até próxima sexta-feira, viu? É isso. Próxima sexta é horário normal, 10 horas. Vai ter professor Gilson Gonçalves dos Santos, que vai dar palestra.
Ok, professor.
Eu vou encerrar aqui, tá? Vai ter outra reunião.
Ok, bom fim de semana.